Alright, so here we are with the 4-8 notes for geometry. This is an introduction to coordinate proofs, so we will be doing that. Coordinate proof means it's going to be on the coordinate plane, so we're putting shapes on the coordinate plane to do a coordinate proof in order to prove that something works. The interesting part about coordinate proofs is that you position the figure kind of down by that axis of the y-axis and the x-axis intercepting in order to kind of make it applicable, okay? And it also is going to use these geometric concepts, and so most of this won't actually have necessarily numbers, but more ideas that you could put numbers into. So we are only doing an introduction here, so just kind of an overall view of how to set this up. So first thing, you have used coordinate geometry already. We've talked about midpoints, and midpoints is that middle distance between a segment, for instance, of the segment endpoints. And then we've also found distance, so we have those formulas that we know from actually the first section. Then we talk about coordinate geometry and the fact that it can be used to prove conjectures. And so conjectures is this idea that uses variables. So for instance, we'd see a shape and we'd say the length of this is b versus 7. Okay. So on that, in the coordinate proof, it's a style of proof that uses coordinate geometry, meaning we get some coordinates involved and we have it on a grid. And then, of course, the algebra that goes with that. The first step of a coordinate proof is to position, as I just mentioned, kind of by that 0, 0 origin, the given figure in a plane, so you can use any position, but some strategies, of course, make sense. For instance, anytime you have a rectangle, it's nice to kind of put that 90 degrees where you would see one. So here are some strategies or ideas for when you are setting up where this shape could be, because it's not just going to be on a plane, it's going to be on a coordinate plane. So definitely a good idea to use the origin as a vertex, so as one of those meeting points of the sides. Always wanting to keep this in quadrant 1 if you can, nice positive numbers or values. You could also center the figure at the origin, so maybe when we're thinking of a circle, it's nice to have that middle point. Center of side of the figure at the origin, so it's nice to at least have one axis along a side, and then that's kind of what this last one says. Use one or both axes as sides of the origin. Alright. So here we are positioning a figure. As you can see, we've got the image already, but because it is a square, remember that squares have 90-degree angles. And so it makes sense, hopefully, that a y-axis and x-axis that meet at 90 degrees should be where one of the corners of the square is. This one does in fact use numbers, and so notice that they're saying 6 units. So as long as you have 6 squares here covered and then the end of the line, that's going to be the same down as well because it's a square. And then of course this corner is at 90 degrees here. Things that'll help with this is that now we can kind of, for instance, find this length. We can also find its slope. So there's kind of a lot of different things now that we can do that we couldn't do with just a shape on a blank surface. So this first example, and there ends up being some of the images provided already here. So we're making a right triangle. So guess what? That right angle ends up being at the origin. One of the leg lengths is 2, and so you could actually have made it this way. But as you can see, the example that our text is giving here has the higher side on the y-axis and then the shorter side on the x-axis, which is fine. So they are telling you to use the origin as the vertex of the right angle, again, because it would not necessarily make sense to have it go over here, because then you can't necessarily be completely sure that this is 90 degrees. So best to put it at the origin. Alright, so once the figure is placed in the coordinate plane, you can use slope. For instance, we've been talking about sides being parallel and things like that, and so now instead of having to use alternate interior angles, we could use same slopes, because if slopes are the same, then we have parallel sides. Another thing in your proofs here is that maybe they don't have to say that something is a midpoint. You can still use the definition of midpoint, because now you can calculate if that actually is the middle. Or, for instance, the vertices, you can find the distance between them and talk about, for instance, a triangle being congruent by side, 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 just because of the distance formula. So, looking at our second example here, we're going to write a 2-column proof, and it's got a rectangle. So as you can see, as the rectangle was set up, definitely set up so that one of its vertices, which would be right, is at the origin. And then we're actually kind of foreshadowing, because this is actually something that we'll be using a lot in Chapter 7, but the diagonals, it turns out, bisect each other. So I would, for instance, know that this piece and this piece would match in length, meeting here at the midpoint, and then this piece and this piece match. So, again, the only thing is given is that it's a rectangle, and then it has these coordinates. And so from there, from that original starting point, we're going to go ahead and talk about proving the diagonals bisect each other. So to start off this proof, we do want to actually find the coordinate of this. Not too hard to find out that it's over 2 up 5, but we do want to make sure that even though this diagram seems pretty to scale, we do want to actually use the midpoint formula to prove, okay? Because proving is not the same as see, I did it. Okay, so in that case, we've got our midpoint, and so if we put the coordinates of A here, 0, 0, and the coordinates of C, which would be 4, 10, if we put them in, we get 2, 5 as our center. Same thing happens with BD, so if we put in the coordinate of B, which is 4, 0, and then the coordinate of D, which is 0, 10, we end up adding, dividing by 2, finding that average, and we get the same midpoint of 2, 5. So because of this statement, we do now know that if 2, 5 is the middle of this piece, those two pieces are the same. And by the definition of midpoint, if that dot is in the middle, then those two are the same. And so since the midpoints coincide or are the same, the diagonals must have to bisect each other, because they meet at that point. Alright, so coordinate proof can be used to prove that a certain relationship is always true. And again, that is because we are going to replace numbers with letters. If you replace it with letters, you end up getting this statement that's true no matter what orientation the shape is in. So, you can prove that a statement is true for all right triangles without knowing the side lengths. Again, to do this, you assign variables as the coordinates. So, for instance, instead of knowing exactly that this is a distance of 4 over, we could just replace 4 with B, okay? Because that's just a letter that we know represents, in this case, 4, but it just represents any number that could work. So looking at our third example, we're going to assign coordinates to vertices. Anytime you can use 0 in any of these problems, very helpful, because zeros tend to cancel. So we're supposed to position this rectangle in the coordinate plane and give the coordinates of the vertex. So it's a rectangle, it has a width of m. So notice here, we've made this a distance of m. To get to it, you technically go over none and up m. Then they give us this second piece that says, hey, the length is twice the width. So 2 m's, which is what's given here, and then up nothing would give us to this coordinate. And with that idea for the length, to get all the way up to the corner here, you'd go over 2m and up m. So again, we have now decided that if you have a rectangle with a width that ends up doubling to get your length, we actually could talk about pieces of it, like what is its midpoint going to be if we just knew m. So this problem again was just asking for all of the coordinates. Alright, next one, they want you to take this right triangle. Notice they've put the right at the 0, 0. And it's got lengths of s and t. And so it doesn't necessarily say if s is bigger than t or even if s equals t, which would hopefully just mean you use the same letter. And so in this case we've just sketched that t is whatever that length happens to be, and then S is whatever this length happens to be. Because it doesn't actually matter what the lengths are as long as we can kind of visually see that it would make a triangle. Because of course the length isn't going to be a negative number. So just be careful when you're making your coordinates, because again we're going over T, which is the first piece, and then up nothing, so that's here, versus writing this as S0 or something. Alright. We got to be careful. We don't want to use both axes when positioning a figure unless you know the figure has a right angle. Okay, because the intersection of a vertical line and a horizontal line, or the x-axis and the y-axis, is going to be at 90 degrees. In this next example here, we're positioning a square with side lengths of 4p. Okay, maybe they're going to end up talking about breaking it up into p pieces, whatever it happens to be. But again, the idea is if it's a square, to go over 4 and up 4p, you'd be at that corner. We also know we can position it at 0, 0 because we have a 90 degree angle in every square. And then again, just being careful that you graph in the correct order. So over the amount, in this case 4p, and then up nothing, versus over nothing, up 4p. That was supposed to be over. Alright. So if coordinate proof requires calculations with fractions, we're going to choose coordinates that make calculations simpler. So again, if you kind of think of this and then talking about a midpoint, it's nice that there's 4p instead of p divided by 2 to get in the middle here. Because instead then you'd have 2p. So it might mean that we're going to try to break this up into p pieces. And so 1/4 of a p is a whole lot more complicated to look at than just a p by itself. So trying to avoid fractions as much as possible. Multiples of 2 when you are finding coordinates of a midpoint is always helpful. So if you have a distance and they're saying that you're going to end up finding a midpoint, make it 2m or 2x length. Once you've assigned the coordinates of the vertices, the procedure for the proof is the same, except that your calculations will involve variables. And of course it'll feel a little bit more stressful in the math because you can't really simplify much. But it's okay. So remember, because the x and y axis intersect at right angles, again, they can be used to form the sides of a right triangle, but not necessarily any other triangle. So here we are with a coordinate proof. This is going to be the same steps as our previous example, which used this one, example 2. Okay, because they're saying, hey, guess what? There's some diagonals of this rectangle, and the diagonals are congruent. In this case, it's not going to be midpoint necessarily, but we are going to end up using a formula, in this case, distance formula, in order to say that the diagonals from QS to PR are congruent. So, first thing we're going to do is kind of assign that this is in our coordinate plane, on an x-axis and a y-axis meeting at 0, 0. The coordinates of P here, apparently they've decided this length of this side is B. And so to get up to P, you're going to go over nothing and up B. The next thing is that the coordinate of Q comes from the fact that we've decided this length is A. And so this is A0. And so to get up to Q, you go over A and up B, whatever those lengths happen to be. So we've positioned the figure in the coordinate plane here, and so now we have this visual that we can use in order to find the distance between SQ, and then that's distance between PR. So here's our image that I drew in the previous one, but now it's just coordinates. And in order to write the coordinate proof, we're going to go ahead and get the distances. So notice that this is already kind of given for us. PR is a squared plus b squared, and QS is a squared plus b squared. two ways of doing this, and in fact the easier way is the fact that this is a right triangle. So instead of using the distance formula, I can just say this side squared plus this side squared is going to equal this diagonal squared. So if a squared plus b squared is going to equal c squared, how do I get c by itself? I square root both sides, which would of course leave c by itself. Same thing happens for the other side. We still have a side length of b and a side length of a. And so b squared plus a squared is going to equal that diagonal squared. Of course, square rooting means that you're going to have a squared plus b squared square rooted. So again, not a number, but clearly you can see that these two distances are the same, are congruent. So eventually, if you are then given these side lengths of a triangle, you can plug them in for A, plug them in for B, and you will know that the diagonals are congruent. So, taking a look at some of our examples here at the end, we're going to position each figure in a coordinate plane. We have a rectangle with a length of 6 units and a width of 3 units. So depending on how you imagine length and width, our length is 6 and our width is 3. And so as much as that was helpful when we were making diagrams, we now want to actually mention the coordinates. So over 6 up nothing, over nothing up 3, and then over 6 up 3. And then of course at 90 degrees for our origin. The next one has a square with side lengths of 5a. So we've got our origin. We've got our square, of course, at 0, 0. And so the coordinates are going to be 0, 0, and then over 5a up nothing, over nothing up 5a to get to this point, and then double, so 5a and 5a again to get all the way over to that other coordinate, or corner is what I'm looking for. So the last part here is a tiny proof. We've got rectangle ABCD with coordinates given here. E is the midpoint of BC, and F is the midpoint of AD. And so all we need to do is find the length of EF and AB, because we're going to say that they are congruent. So a little diagram of what we have here. This is apparently where A is. B is over nothing up 8, so this is apparently where B is. I'll just make that into a B. D is over here at 5, 0. And my rectangle looks a little bit more like a square, but that's okay. So C is 5, 8. Again, I'm not using a ruler to talk about this one, I'm using the math, so if I drew it kind of awkwardly, there you go. So, E is the midpoint of BC, so let's see, BC, we're going to call whatever the midpoint is here. I don't know the coordinate right now, but I do know that it will break it in half. And then we also have F as the midpoint of AD. Again, those two pieces matching. Which will then, because I don't know many rectangles that end up sinking in the middle, we are trying to prove that EF is going to be the same as AB. Kind of stating that, again, it's like a perfectly risen cake or something like that. So, how do I find the length between EF? I need the coordinates of EF. So E, since it's the midpoint of BC, means that I'm going to do the midpoint formula. And so the midpoint formula says that I'm going to take my x's, which are 0 and 5, add them, divide by 2, and take my y's, add them, and divide by 2. And that is going to be coordinate E, which is going to be 2.5 and 8. Which hopefully makes sense because it has to go up as high as the other ones. Alright, the other piece, we're going to find the coordinate of F. So the midpoint, or the coordinate of f, comes from our x's being added and averaged, and then our y's being added and averaged. And so we get 2.5 and 0 for f. So we have now gotten the coordinates of these two, which is in the middle, and so now I need to find the length of this side just as much as I need to find the length of this side. So the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So if I'm going to find the distance between EF, I need to take my x2, I'll call this x1 and y1, and this x2 and y2. So I need to take my x2 and subtract my x1, so 2.5 minus 2.5. And then the y2, which is 8, minus the y1, which is 0. And so we end up with 0 squared plus 8 squared. And so 0 squared is 0, 8 squared is 64. And so the square root of 64 gets us 8 as the length of EF. So then we do one more distance, and now we're doing the distance for our side. And of course we could count it, but remember that we're trying to do this kind of properly versus just by looking. And so in this case, the distance between AB is going to be reflected in our x1 and x2 and y1 and y2. So our x2 is 0 and our x1 is 0. And our y2 is 8 and our y1 is 0. So hopefully you can see that this very much simplifies the same way. We've got 0 squared plus 8 squared. And so the square root of 0 plus 64, square root of 64, or 8 again. And so now that we have 8 as AB and 8 as EF, we can say that EF is the same as AB. So, how do we find that? We found the midpoint, found the distance between the midpoints, found the distance between the side, and so now I'm saying that that middle of the rectangle is the same height as the side of the rectangle. Alright, so that's a little bit of an intro into coordinate proofs, and again, the main idea is that we are trying to find a relationship that's always true, and so that's why the variables come into play.